Welcome back to the lectures on drone systems and control. In the last lecture, we have seen, we have gone through the details of technical knowledge on state space representation of control systems. So, the topics are getting evolved like this. First, we talked about differential equation which can represent a system mathematically. Then we see that if we convert the differential equation into algebraic equation, then there are certain easier way to analyze the system in the form of poles and zeros, and then we can check the responses based on those. We can talk about the natural frequency of a system, specifically for a second order system, then its damping ratio and all. So, we got to know about the transfer function. Then we came to the topic on state space analysis or state variable analysis, which is another form of representation of the system, and it has certain benefits over transfer function, right? Okay. So, now in this particular lecture, we will see or we will go through the Matlab demonstration of transfer function and state space interchangeability. Okay. That means, if we have a transfer function for a system and we want to analyze the system in a state space form for its inherent benefits, then how to convert the system into from transfer function representation to state space representation, and vice versa. That means, sometimes if we have the state space representation, that means the matrices which represent the system, having those matrices, how we can generate transfer function, and then we can have the pole zero plot and all. Okay. So, we by this time we know that both transfer function and state space analysis have significant importance in the study of control systems and in the process of analyzing the performance of systems, right. Okay. So, just to have a basic recap, we remember that the transfer function is a Laplace domain representation. It is no more a time domain way of representing a system. It expresses the system as a ratio of output to input in the Laplace domain or S domain, right. When it is S domain, we know that S is equal to zeta plus j omega. So, when we have the transfer function from the numerator, we can get to know that whether there are zeros in the system, right, and from the denominator we get the poles of the system. How? If we make the numerator polynomial equal to 0 and solve the equation, then it gives us zeros. At the zeros, the transfer function of the system becomes 0, right. Now, if we make the denominator polynomial equal to 0, what we get? We get the poles. At poles, what happens? The transfer function will become infinity, right. So, when we have S domain representation with sigma and j omega, then if we have two different poles like this, say one is at the location -1, another is at location -3, then we can say that there will be this is a kind of system, it will have its specific transient response. If we have the poles, both the poles in the, say, in this place, then it will be conjugate, complex conjugate poles, then we will get a different type of system response. So, transfer function gives us the freedom to analyze the system in S domain, right. Now, what happens in state space representation? Okay. For state space representation, we have state equations which is in this form. What is x? X is the state vector. What is u? It is the input vector. Okay. And what we get here is actually a differential equation, but in terms of system matrix and input matrix. Okay. So, x is a state vector, then u is the input vector, A is the state matrix and B is the input matrix, and it has its own dimensions accordingly. Now, the second one is output equation, where we have a form yt equal to cxt plus dut. Again, we know that x and u, the definitions are state vectors and input vectors, and what is y? Y is a column vector for output variables. Okay. Then C and D have their designated dimensions. Okay. So it is interesting to check that if we have a system which is, say, represented in a transfer function form, that means Gs equal to, say, Ys, that is the Laplace transform of output, and here Laplace transform input in the numerator, right? Then we can see that this is the transfer function representation and this is the state space representation with the state equation and output equation. How we can convert a system with transfer function representation to state space, and then from state space to transfer function in Matlab, that we will see. Okay. The theoretical concepts how to transform the systems from one form of representation to another form of representation, the students can read from the teaching materials which we have provided, the books, textbooks which we have referred. So they can have the theoretical understanding from the study materials, but when it comes to Matlab, I will show that how we do this. Okay, fine. Okay. So first we will see that if we have a transfer function, okay, then how to change the system. Okay. So let's see that how to define a system in terms of transfer function. We should have numerator, right? So we take one system which has the numerator as 1 and 2. What does that mean? It means that the system, the particular system which we are talking about, has a 0 at -2, right? Try to think about it. Okay. Now we specify the denominator. The denominator I write as 1, 2, 5. Then what is the denominator of the transfer function? It is s square plus 2s plus 5, right? Okay. So we have the numerator and denominator. We want to see how the system looks like. How to do that? We know that we have to write this particular command, right? So if we run it, we'll see that we have the numerator polynomial as s plus 2, the denominator polynomial as s square plus 2s plus 5, right? What does that mean? There is a 0 at s equal to -2, and accordingly if we solve this particular polynomial making s square plus 2s plus 5 equal to 0, then we get the poles accordingly, right? So we know how the system looks in a transfer function form. So when we talk about the transfer function of the system, what we see? We see that with the system looks like in transfer function form, it looks like s plus 2 by s square plus 2s plus 5. It is a continuous time transfer function, okay, not in a discrete domain. Okay. Now we do not want to see this in the command window further. What we will do is that we will try to get the state matrices. Okay. Sorry. And the command through which we can say get this particular state space representation is TF to SS. Okay, that means transfer function to state space. Just remember that this TF to SS function should have two arguments inside. So you have to write it in the form of numerator and denominator. Okay, we put it like this. If you are putting only system, then it will not work. Okay. Now when we simulate this one with TF to SS, then we get the matrix like this. First we get the matrix A, which should look like this. The second one should be B, right. Third one is something like this, fourth one is 0. Okay, fine. So, this is what it happens when we try to see this system and simulate it to get the transfer function from transfer function form to state space representation. Okay. So, this is what you can do by having your own system and then transforming it into a different level or different set of representation. Okay. So, this is what we get as the system matrices A, B, C and T. Okay. Now, if we want to come back from the particular system, if we have something like we will specify this matrix, okay, and we want to come back from the particular state space form of ABCD to the transfer function form, then how do we do? Then we will do it like this. Okay. Say we will just write it in terms of N and D, just to emphasize the fact that N becomes num that we have set previously and D becomes denominator that we have specified as this. Okay. Fine. Now, when we are converting the system from say transfer function to state space, right, then we have to do TF to SS. When we doing it from the other side, that means when we have state space and we will convert it to transfer function, then what we have to do? We will write it as the command will be SS to TF. Okay. What we are going to write here? We will write A, B, C, D. Okay. Fine. So, from this we can see that we are getting the numerator and the denominator for the transfer function as we specified. Okay. So, once we get it, it will be easier for us to like take some other matrices or some other transfer functions and convert back and forth. One is from transfer function to state space, another will be from state space to transfer function. When you have to design a controller in say PID control system, you want to device for a particular drone, then sometimes it might be easier to do it use the transfer function form. Sometimes you can explore the state space systems as well. So, with this it is kind of giving you the indication that how the systems look like in this way. Okay. Fine. So, I request the student that you explore your own problems, just create one transfer function and then convert it to state space representation. Similarly, you just take some state space matrices like A, B, C and D, whatever you want to specify, you just do that and then see whether you are getting a transfer function, and from that transfer function what you can analyze, whether it is a first order system or second order system or third order system, where the control input will come, which is going to be the which input is actually being the or serving as a control input in the system, okay, which state is serving in that way. So, you have to analyze the systems as per its requirement, and I encourage you to solve as many problems as possible. The suggestion will be that first you take a system say A, B, C, D and mathematically try to find the transfer function. Also, you explore the MathWorks software to understand that whether what you are getting mathematically is the same as what the software is giving, whether you are doing some error or not. So, in this way I think you have to study, so that you have a kind of mathematical knowledge, and at the same time there is a software support, so that you can collaborate and can understand the system in a better way. Okay. Thank you, welcome, and we see you in the next lecture.